What is good, everyone, and welcome back. Today we are building and deploying Project Alabama from scratch. Project Alabama is a full-stack AI security operations console. It ingests enterprise log files, detects insider threats using rule-based anomaly detection, and uses Google Gemini to turn raw security alerts into plain language analyst reports. Next.js on the front end, Prisma and Neon on the back end, and Gemini handling the AI layer. We are going to go through the entire code base, demo the finished app live, and then deploy it to a real domain using Hostinger, who are sponsoring today's video. This is a long one, so let us not waste any time. Let us get into it. Before anything else, quick word from today's sponsor, Hostinger. We are using Hostinger to deploy Project Alabama today, and I want to show you exactly how the process works because it is genuinely straightforward. Head to hostinger.com. Link is in the description. You want the cloud hosting or VPS plan. For a Next.js app like this one, the cloud plan is the right starting point. It handles the build pipeline, gives you enough resources for real traffic, and the pricing is very fair. Click Get Started, pick your plan, and when you hit checkout, use my coupon code in the description. It gets you a solid discount off your first purchase. Make sure you apply it before you pay. Inside the Hostinger dashboard, you connect your GitHub repository, set your environment variables, and hit deploy. For Project Alabama, that means 4 environment variables: database _URL, direct _URL, Gemini _API _key, and Gemini _model. It pulls your code, installs dependencies, builds the app, and serves it. No custom config files, no build scripts to write. What I like about Hostinger specifically for a project like this is the visibility. Logs are right there in the dashboard. If a build fails, you see exactly why straight away. And when the app is live, monitoring is built in. Link is in the description. Coupon code is right below it. Now let us build the thing. Before we walk through the code, let me show you what we are building so you know exactly where we are headed. This is Project Alabama running live. The Alerts tab is the main view. At the top, you have 4 KPI numbers: total events ingested, total alerts, open alerts, and critical alerts. The open pressure bar gives you a quick visual on how much active risk is sitting in the system right now. Let me hit seed demo to load the curated dataset. Watch the dashboard populate. You can see alerts appearing in the list in real time. Click on any alert and the detail panel opens on the right. You can see the user, the trigger event, the device, the IP, and the location. Below that are the detection signals, the specific rules that fired, and why this alert exists. This one has 2 signals firing together: download spike and off-hours privilege action. The combined risk score pushes it to high severity. Now click Generate Explanation. This calls Gemini. In a moment, you get a headline, a full analyst-style write-up of what happened, and 3 concrete recommended next steps. Gemini is reading the actual alert context every time. This is not a template. So now, over on the Log Upload tab, you can drop in a CSV, JSON, NDJSON, or key value log file. The parser auto-detects the format, normalizes the rows, runs the detection engine, and Gemini summarizes the upload with the top risks found. The raw ingest tab lets you paste JSON directly. The sample payload in there already triggers 2 detection rules simultaneously, so you can see it fire right away. That is the finished product. Now let us build it. We are about setting up Project Alabama. This is a security operations console built with Next.js, Prisma, and Neon as the database. By the end of this video, we will have the full app running locally, and we are going to walk through every major file in the Codebase so you know exactly how everything fits together before we start building. Let us get into it. We start by cloning the starter repo. Head to your terminal and run git clone with the Alabama starter repository URL. This pulls the entire project scaffold down to your local machine. Once that is done, change into the project folder and run npm install. This pulls in all the dependencies. Next.js, Prisma, the Neon driver, everything the project needs. Depending on your connection speed, this might take a minute, so just let it run. While that finishes, we need to set up our environment variables. Create a new file in the project root called .env.local. This is where all sensitive config lives. Database URLs, API keys, anything that should never get committed to Git. The git ignore in the starter repo already excludes this file, so you are safe. Now for the database, open your browser and navigate to the Neon console. If you have not used Neon before, it is a serverless Postgres provider. It works really well with Next.js because it handles connection pooling automatically. Create a new project and name it Alabama-proj. Once it is created, Neon gives you a connection string. Copy that string. Go back to your .env.local file and paste it in twice, once as database_URL and once as direct_URL. So the reason we need both is that Prisma uses database URL for the pooled connection and direct URL for running migrations directly. If you only set one of them, your schema push will fail. So make sure both are there. Now run npm run Prisma generate. This reads your schema file and generates the typed Prisma client. All the TypeScript types and query builders you will use throughout the app get created here. Anytime you change the schema, you need to rerun this command. Next, run npm run Prisma push. This takes your local schema and pushes it to Neon, creating all the tables in the database. In a production setup, you would use migrations instead, but for local development, push is the fastest way to get your database in sync. Alright, everything is wired up. Run npm run dev to start the development server. Open your browser and go to localhost 3000. Now, you should see the Alabama Security Ops console load up. Take a look at the tabs across the top. We have alerts, log upload, raw ingest, and integrations. Each of these maps to a distinct feature area that we will be building out in upcoming sections. Now let us walk through the code base. Open prisma/schema.prisma. This is the heart of the data layer. It defines 4 core models. The event model represents normalized log entries, things like user logins, file downloads, and API calls. Raw activity from various sources gets normalized into this shape. The anomaly model captures rule violations. These are individual suspicious behaviors that the detection engine has flagged. The alert model aggregates those anomalies. When multiple anomalies cluster around the same user or the same time window, they get promoted into an alert that an analyst actually needs to act on. And finally, the integration connection model stores configuration for external services, things like connecting to a SIEM or a ticketing system. Next, open lib/types.ts. This file contains all the TypeScript interfaces and enums used across the application, entity shapes for events, anomalies, alerts, and integrations, plus enums for event types and severity levels. Anytime you want to understand what shape a piece of data has as it moves through the app, this is the first place to look. Quick one now. Open lib/db.ts. This just initializes the Prisma client using a singleton pattern. That means you are not creating a new database connection on every single request. This matters a lot in a serverless environment like Next.js. Now open lab/detection.ts. This is where the interesting stuff lives. This file contains the logic for all the security detection rules. Each rule has a name, a condition, and a scoring weight. For example, impossible travel. If a user logs in from two geographically distant locations within a short time window, that gets flagged. If a user downloads an abnormal volume of data in a short period, that scores high as well. These weights feed directly into the anomaly scoring system. So now open lib/store.ts. This is the data access layer. All your CRUD operations live here, creating events, querying alerts, updating statuses. The rest of the app calls functions from this file rather than writing raw Prisma queries in line. It is a clean separation that makes the code base much easier to test and maintain. Now this one is really cool. Open lib/gemini.ts. This is the Gemini AI integration. When an alert is generated, instead of just showing raw data to the analyst, the app calls Gemini to produce a natural language explanation. So instead of a list of anomaly scores, the analyst sees something like, this user accessed sensitive files from an unrecognized location immediately after a failed login attempt. That kind of context is huge for how fast an analyst can triage an alert. Last two files, lib/log-file.ts handles parsing for uploaded log files. Different log formats come in from different sources, and this file normalizes all of them into the event shape we saw in the schema. And lib/integrations.ts manages the connection logic for external services, authentication flows, API calls, and status checks for anything connected through the integrations tab. Next up, the API routes. Open app/API/ingest/upload/route.ts and app/API/ingest/route.ts. These two endpoints are responsible for taking in security log data. The ingest route accepts raw JSON payloads directly, while the upload route handles file uploads in formats like JSON, CSV, and NDJSON. Both routes need to validate the incoming data, normalize it into a consistent shape, run the detection engine against it, and finally persist everything to the database. You will see to-do comments throughout marking exactly where each of those steps goes. Now open app/API/alerts/route.ts. This is a get endpoint. It fetches all alerts from the database, ordered newest first, and also pulls system-wide stats like total event count, open alerts, and critical alerts. The dashboard pulls this every 12 seconds to stay current. Next, open app/API/alert/id/explain/route.ts. This is where the Gemini AI integration lives. When an analyst clicks Generate Explanation on an alert, this endpoint takes the full alert context, including the anomalies that triggered it, the event metadata, and the risk score, and sends all of that to Gemini. Gemini returns a plain language explanation plus suggested next steps. And if Gemini is unavailable for any reason, the app falls back to a deterministic rule-based summary, so the experience never breaks. Next, briefly check the three utility routes. App/API/integrations handles cloud provider connection state. App/API/seed resets the database and loads a created set of demo events designed to trigger all four detection rules. And app/API/reset wipes everything clean so you can start fresh. Now let us move into the state and component logic. Open hooks/use dashboard state.ts. This custom hook is the brain of the entire dashboard. It owns all React state, all API calls, and all derived values. When you look at the page.tsx file, it is intentionally thin. Its only job is to call this hook and pass the results down to child components. That keeps all the business logic in one testable place. Open app/page.tsx. As I said, this file is intentionally thin. It calls use dashboard state once at the top, then renders the layout shell. The sidebar on the left, the top bar across the top, and the main content area in the center. 4 tab views are conditionally rendered based on which tab is active. Open components /dashboard/sidebar.tsx. This is the fixed left navigation column. It renders the app logo, the 4 nav tabs, quick action buttons at the bottom for the AI session and connecting apps, and a footer showing the currently active Gemini model name. The sidebar holds 0, local state, everything is driven by props. Open component/dashboard/topbar.tsx. The top bar shows the current tab title, an alert count badge on the alerts tab, a toast message showing the last operation result, and the seed demo and reset buttons. Seed demo calls post/API/seed. Reset calls post/API/reset. Now we are implementing the data access layer for Project Alabama. This is the lib/store.ts file, and it is the single most important file in the entire backend. Every API route talks to this file instead of calling Prisma directly. That means all database logic lives in one place and the routes stay clean and small. Let us get into it. Alright, we start by importing the 2 functions we need from the detection module. Run detections and build summary from lib/detection.ts. Run detections is what actually analyzes an event and decides whether it is suspicious. Build summary turns the triggered rule names into a human-readable sentence for the alert. Next, we define 2 internal TypeScript interfaces that mirror the shapes Prisma returns from the database. The first is the event. This is what a raw database row looks like when you pull an event from Prisma. Timestamps come back as JavaScript date objects, not strings, so we need this interface to handle the conversion cleanly. Now, the second is DB alert with anomaly, IDS. This represents an alert row joined with its anomaly links. When we fetch an alert from the database, we get the alert fields plus an array of anomaly ID references. We use this interface to map that shape safely before returning it to the API layer. We also define a few helper functions. Normalize event takes a raw ingest event and fills in any missing fields with sensible defaults. Unknown device becomes the string unknown-device. Unknown IP becomes 0.0.0.0. Unknown geo becomes the string unknown. This means the database schema never has to deal with nulls in those fields. Event2type converts a raw Prisma database row back into the normalized event TypeScript type, converting the date objects to ISO strings along the way. And alert2type does the same thing for alert rows. Now for the main function, ingest events. This takes an array of ingest event objects and processes them one at a time. For each event, it does 4 things. First, it normalizes the raw input using our normalize event helper. Second, it calls prisma.event.create to persist the normalized event to the database. Third, it loads all existing events for that same user from the database. This is important. The detection engine needs the full event history to evaluate temporal rules like impossible travel and download spike. You cannot detect whether travel is impossible if you only have one login. Fourth, it calls run detections with the new event and the full user history. If any anomalies come back, it creates anomaly rows in the database and then creates a linked alert row that ties them all together. At the end, it returns both the ingested events and any alerts that were created. So the API route can report back exactly what happened. Now we have list alerts. This fetches all alerts ordered newest first. Each alert row is joined with its anomaly links, so we know which anomalies triggered it. We then map everything through alert to type to get clean TypeScript types back. Now the get alert with context does more work. This is what powers the detail panel on the right side of the dashboard when an analyst clicks on an alert row. Update alert is simpler. It takes an alert ID, an optional new status, and an optional note string. If a note is provided, it gets appended to the existing notes array. The updated alert is returned, so the dashboard can refresh the detail panel immediately. Reset store deletes everything in the correct order to respect foreign key constraints. Finally, seed demo events. This function builds a curated sequence of demo events designed to trigger all 4 detection rules in a realistic way. For the download spike rule, we create 11 download events for a user named Alice, all within a 30-minute window. Next, we are wiring up all the API routes for Project Alabama. In the last session, we built the data access layer in lib/store.ts. Today, we connect it to the outside world. By the end of this video, the dashboard will be fully live. Data will flow in from the browser, get detected, get stored, and come back as alerts. Let us get into it. Start by opening app/api/ingest/route.ts. This is the raw JSON ingestion endpoint. It accepts a post request containing an array of log events and runs them through the entire ingestion pipeline. So before we call anything on the store, we need to validate the incoming payload. We write a type guard function called isEvent. It takes any unknown value and checks 3 things. First, it makes sure the value is an object and not null. Second, it checks that user ID is a string. Third, it checks that event type and action are both strings. If all 3 pass, TypeScript now knows the value is a valid ingest event, and we can use it safely. Now for the post handler itself. We pass the JSON body from the request. The body can come in 2 shapes, either a plain array of events or an object with an events array nested inside. We handle both by checking if the body is already an array, and if not, we try to pull body.events. So if the array is missing or any item fails the isEvent check, we return a 400 error with a clear message explaining the expected shape. No silent failures here. If validation passes, we call ingest events from the store. That function normalizes each event, saves it to the database, runs the detection engine, and creates alerts for anything suspicious. We return the ingested count, the alert count, and the created alert directly in the response. Now open app/api/alerts/route.ts. This is the get endpoint. The dashboard polls every 12 seconds. It needs to return 2 things at once: the full list of alerts and the system-wide KPI stats. We use promise.all to fetch both in parallel. Get system stats and list alerts run at the same time instead of one after the other. On a code request that could save 100 milliseconds or more. We also set the dynamic export to false dynamic at the top of the file. This tells Next.js to never cache this route because alert data needs to be fresh on every request. The response shape is simple: a stats object and an alerts array. Now open app/api/alerts/id/route.ts. This is the dynamic route for a single alert. It has 2 handlers. The get handler takes the alert ID from the URL params, calls get alert with context from the store, and returns the full alert with its anomalies, the trigger event, and the related event timeline. If no alert is found for that ID, we return a 404. The patch handler lets analysts update an alert. We pass the body for two optional fields, status and note. We have a small statuses constant array containing the three valid values, open, investigating, and resolved. If the client sends a status value that is not in that array, we reject it with a 400 error immediately. If validation passes, we call update alert from the store and return the updated alert. Next, we are building the AI layer for Project Alabama. This is the feature that takes a raw security alert and turns it into something an analyst can actually act on. Instead of staring at a list of anomaly scores, the analyst gets a plain language explanation of what happened, why it is suspicious, and exactly what to do next. All powered by Google Gemini. Let us get into it. Start by opening lib/gemini.ts. Before writing any logic, we define the two TypeScript interfaces that describe what this module returns. The first is explanation result. This is the shape of the AI response for a single alert. It has four fields: a headline, which is a short one-line summary of the threat, an explanation, which is the detailed analyst-style write-up, a next steps array, which contains exactly 3 recommended actions, and a meta object, which tracks which Gemini model was used, whether the fallback was triggered, and any error message if something went wrong. The second is upload insight result. This is the shape for the upload summary feature. It has a summary string, a risks array of up to 3 items, and the same meta object. These interfaces are important because they give the rest of the app a guaranteed contract. Whether the response comes from Gemini or from the fallback, the shape is always identical. Now we handle the API key and client setup. Open the browser and go to AI Studio at aistudio.google.com. Create a new API key and copy it. Back in the project, open .env.local and add a new line. Gemini_API_key equals your key. Optionally, you can also add Gemini_model to set a default model. If that variable is missing, the code falls back to Gemini-3-flash-preview. Back in Gemini.ts, we import Google Gen AI from the @google/Gemini package. Now we write the fallback function. Fallback explanation takes an alert with context and a meta object. It builds a deterministic response from the data we already have without calling Gemini at all. The headline uses the risk score, severity, and user ID. The explanation lists the anomaly reasons line by line, then adds the trigger event action and resource. The next steps are 3 standard investigation steps that apply to virtually any insider threat scenario. Validate the account owner, initiated the activity, check endpoint and identity logs for compromised credentials, and review the timeline for lateral movement and data exfiltration patterns. This fallback is not a placeholder. It is a real useful response. The goal is that even with no Gemini API key at all, the feature still works. Now the main function, explain alert with Gemini. It takes 2 arguments, the full alert with context and an optional model override string. The model resolution order is the override if provided, then the Gemini_model environment variable, then the hard-coded default. Before doing anything expensive, we check 2 things. First, is the API key present? If not, return the fallback immediately with an error message saying the key is missing. Second, is the model name format valid? We run it through a simple regex that allows letters, numbers, dots, hyphens, and underscores. between 3 and 120 characters. This prevents injection attacks and catches obvious typos before they reach the API. If both checks pass, we instantiate the Google Gen AI client and build the prompt. The prompt is an array of strings joined with new lines. We start by telling Gemini it is a senior SOC analyst for insider threat detection. We tell it to return strict JSON with exactly 3 keys: headline, explanation, and next steps. We give it explicit rules. The explanation must be concise and actionable. Next steps must contain exactly 3 short strings, and there must be no markdown, no code fences, only a raw JSON object. Then we append the full alert context serialized as JSON. Now we handle the response. After calling AI.models.generate content, we get back a response object. We pull out the text field and trim it. Here is where extract JSON object comes in. AI models sometimes wrap their response in markdown code fences like triple backtick JSON. Extract JSON object strips all of that away. It first checks if the text already starts and ends with curly braces. If it does, it returns it as is. If not, it uses a regex to find the first JSON object shape in the string, pulling just the part between the outermost curly braces. We pass the cleaned text into save pass explanation. That function calls json.pass inside a try catch. After passing, it validates that the result has a headline string, an explanation string, and a next steps array where every item is a string. If any of those checks fail, it returns null. If save pass explanation returns a valid result, we spread it into the return value and attach the meta object with used fallback set to false. Done. If it returns null, meaning the model returned something we could not pass, we call fallback explanation with an error message saying the model response was not valid JSON. So now, if the entire API call throws an exception, we catch it and call pass Gemini error. That function looks inside the error message for a structured Gemini error payload. The second exported function is summarize upload with Gemini. It works almost identically, but is designed for the log file upload feature rather than individual alerts. It takes the file name, the detected format, the event count, the alert count, and an array of the top alerts as context. And that is the complete Gemini integration for Project Alabama. 2 exported functions, a robust fallback that always produces a usable result, strict JSON prompting to keep responses consistent, a regex-based JSON extractor to handle markdown wrapping, structured error, passing with human-readable messages, and a model name validator to prevent bad inputs reaching the API. Now open app/api/alerts/id/explain/route.ts. This is the post endpoint the dashboard calls when an analyst clicks generate explanation. It reads an optional model field from the request body wrapped in a try catch because the body is genuinely optional. It calls get alert with context to load the full alert with its anomalies and related events. If the alert does not exist, 404. Otherwise, it passes everything to explain alert with Gemini and returns the result directly. Now the log file parser, openlib/log-file.ts. The main export is pass uploaded log file. It takes the raw file content as a string and tries 4 parsers in order until one succeeds. The parsers are parser.json, parser.ndjson, parser.csv, and parser key value logs. We are building 2 more API routes for Project Alabama. The AI explanation endpoint that powers the generate explanation button in the dashboard, and the integrations management endpoint that handles connecting and disconnecting cloud providers. Short video today, but both of these routes tie together a lot of the work we have done in previous videos. Let us get into it. Now open app/api/integrations/root.ts. This root handles two things: listing all integration connection states and creating or updating a connection. Start with the imports. We need list integrations and upset integration connection from lib/integrations.ts and the integration provider and integration status types from lib/types.ts. At the top of the file, we define two small constant arrays. Providers contains the 5 valid provider names: AWS, GCP, Azure, GitHub, and Slack. Statuses contains the 3 valid status values: connected, disconnected, and error. We use these for validation in a moment. The get handler is simple. We call list integrations and return the result wrapped in a JSON object with an integrations key. The interesting thing about list integrations is what it does when a provider has never been configured. Rather than returning an empty list, it returns a virtual disconnected record for every provider that is missing from the database. So the get handler always returns exactly 5 cards, 1 for each provider, regardless of whether anyone has ever connected anything. The dashboard integrations tab always shows all 5 cards with their correct connection states. So now the post handler is more involved. We pass the JSON body inside a try catch. If the body is not valid JSON, we return a 400 immediately. Then we validate 2 fields. First, provider. It must be present and must be one of the 5 values in our provider's array, if not 400. Second, status. It must be present and must be one of the 3 values in statuses, if not 400. These 2 checks are the entire security boundary for this endpoint. If a caller tries to pass an arbitrary string like super secret cloud or an invalid status like pending, they get rejected before anything touches the database. If both fields are valid, we call upset integration connection with the provider, status, display name, and metadata from the request body. In the next session, we do a full end-to-end live test. We seed the demo data, generate AI explanations for real alerts, upload a CSV log file, and watch everything flow through the dashboard live. This is Project Alabama running live. The Alerts tab is the main view. At the top, you have 4 KPI numbers: total events ingested, total alerts, open alerts, and critical alerts. The open pressure bar gives you a quick visual on how much active risk is sitting in the system right now. Let me hit seed demo to load the curated dataset. Watch the dashboard populate. You can see alerts appearing in the list in real time. Click on any alert and the detail panel opens on the right. You can see the user, the trigger event, the device, the IP, and the location. Below that are the detection signals, the specific rules that fired, and why this alert exists. This one has 2 signals firing together: download spike and off hours privilege action. The combined risk score pushes it to high severity. Now click Generate Explanation. This calls Gemini. In a moment, you get a headline, a full analyst-style write-up of what happened, and 3 concrete recommended next steps. Gemini is reading the actual alert context every time. This is not a template. So now, over on the Log Upload tab, you can drop in a CSV, JSON, NDJSON, or key value log file. The parser auto detects the format, normalizes the rows, runs the detection engine, and Gemini summarizes the upload with the top risks found. The raw ingest tab lets you paste JSON directly. The sample payload in there already triggers 2 detection rules simultaneously, so you can see it fire right away. That is the finished product. Alright, the build is done. let us get it live. Make sure your project is pushed to GitHub on your main branch. Confirm your .env.local file is not committed. Check your .gitignore and make sure env files are excluded before you push. Go to your Hostinger dashboard. Click Create New Project and connect your GitHub account. Select your repository. Hostinger automatically detects that this is a Next.js project. Before you hit deploy, go to the environment variables section and add your 4 variables. Database underscore URL, direct underscore URL, Gemini underscore API underscore key, and Gemini underscore model. Save the variables and click deploy. Watch the build logs. You will see Hostinger install dependencies, run Prisma generate, build the Next.js app, and start the server. When you see the build complete message, the app is live. Copy your deployment URL and open it in the browser. And that is Project Alabama fully built and live. Full stack Next.js app, Prisma on Neon, 4 detection rules, multi-format log file parsing, and Gemini-powered AI explanations, all deployed on Hostinger in one video. If you built this alongside the video, drop a comment with your deployment link. And if you want to see more projects like this, subscribe so you do not miss the next one. Hostinger link and coupon code are in the description. Use it. See you in the next one.